Hello, everybody. Welcome to the afternoon lectures in this first day of the UFSCar Workshop on PDEs, 2022 online edition. We will have two lectures by Professors Ederson Moreira dos Santos and Professor Claudio Alves this afternoon. Let me recall that if you have any questions or remarks, please write it down in the comments place on YouTube. You should log in to do it. We invite you to share your comments or questions with the speaker and all the audience. It's a pleasure for me to introduce Professor Ederson Moreira dos Santos from Universidade de São Paulo, Brazil. He is going to talk about on the solutions of the Hénon equations. Professor Ederson is a member of the Brazilian Academy of Science and a fellow of the research agents CNPq. His deep and interesting results have been given an important contribution to the Brazilian research on PDEs, particularly his studies on Hénon equations and other topics. Welcome, Professor Ederson. It's a great pleasure to have you here with us. Thank you for having accepted our invitation.
Thank you very much, Gustavo. Can you hear me?
Yeah, very clearly.
Thank you very much for the introduction. And I would mention that a colleague of us, a friend of us, would say, now in Portuguese, você usou vela de primeira para defunto de segunda.
Oh.
Okay, thank you. So today,
you deserve that.
I will talk about on the solution of the Hénon equation. And this is, my talk will be based on three papers. One joint work with Wendell that got the PhD degree here in our department, two of them indeed. If you scan these, you go directly to the PDF of the papers. Okay, so two papers from the PhD thesis of Wendell and a paper in collaboration with Filomena Pacella. So this is the outline of my talk. I'm going to show to you the equation, then talk about least energy solutions, then I will shift to nodal solutions, the main motivation for starting this thinking on this class of problems. Then I'm going to discuss about the Morse index, first in dimension 2, and then in dimension n greater or equal to 3. Okay, so this is the so-called Hénon equation. And so we have a weight here. So here is just the power. And here the problem is posed on the Bn stands for the open unity ball centered on the origin, at the origin of Rn. I'm going to consider dimensions n greater or equals to 2. Alpha positive is going to be a parameter, and p greater or equals to 2. So the equation here is superlinear. So the equation was named after a paper of Hénon from 1973, and it was posed for some applications to astrophysics. And it turns out that it is a prototype for fundamental problems on the qualitative analysis of elliptic PDEs. Indeed, here we have a course in our PhD program that essentially is based on this equation because it's many interesting questions can be modeled by this equation. And okay, so again the equation. So it was named after the paper from 1973 of Hénon, but only after 1981, after the work of Ni, it became an object of extensive research in mathematics. This weight here, modifies the consequence of the Pós-Graduação identity. Indeed, there exists a new critical Sobolev exponent. So this is the classical critical Sobolev exponent. And once we put the weight here, the new critical Sobolev exponent depends on alpha and is precisely given by this. And this exponent is the exact threshold for existence of solutions. And indeed, there is a radial lemma for the space H10 rad that was proved by Ni, where he proved this embedding here. So this is the critical embedding. So H10 rad of the ball is embedded in this weighted Lebesgue space here. So you see here the new critical exponent here. And then Ni, indeed, how he proved below this number here, he proved that we have compact embedding, and then he used the mountain pass theorem to prove the existence of a solution when P is strictly below this number here. When P is greater or equal to this number, we may use the Pós-Graduação identity to show that there is no solution. And okay, so some interesting questions on this equation. The first one I would say is concerning the symmetry of positive solution. Indeed, there is a symmetry breaking for least energy solution. This least energy solution positive turns to be positive. Okay, they are signed. So since the weight x alpha increases with x, we cannot use symmetrization or reflections arguments to prove radial symmetry of positive solution. So it's not possible. Indeed, when P is superlinear and below the classical critical Sobolev exponent, and if alpha is sufficiently large, then least energy solutions are not radially symmetric. So this was proved by Smith, Sui, Lem in the case n greater or equals to 2, and later Guillaume and Wang, they gave a different proof and included also the case n equals 1. But there is a residual symmetry for least energy solution, and this was proved by Pacella in 2002 and Smets and Willem in 2003. Well, indeed, these papers, I think they appeared more or less at the same time. We see here 1 year of difference, but I think they are more or less at the same time, from the same time. And least energy solution has the Schwaxxoliated symmetry. We have symmetry breaking. Solutions, least energy solutions are not radially symmetric, but they have a residual symmetry. And okay, many other results, contributions were proved by Pistoia, Grossi, Neves, Gladiali, Badiali, Serra, Grazin, Cao, Peng, Yan, Amadori, Gladiali. By the way, Amadori, Gladiali, they have worked a lot recently on this equation. They have done beautiful work. That and Kubler, Wei and Yang, De Figueiredo, here is Di Jairo and Olimpio, Yagaki, they have worked on similar problems. Okay. And about the symmetry of the least energy solution and the least energy nodal solutions. They have the Schwaxxoliated symmetry, and I would mention that all these people have worked on questions on symmetry for this equation in the least energy solution and least energy nodal solutions. And the results proving the symmetry, here is some of them are work on the break of symmetry, for example. And the results about the Schwaxxoliated symmetry were proved by these researchers here. And just to understand the Schwaxxoliated symmetry, you take the maximum. Suppose that the solution U attains its maximum at x0. Okay, so this is x0 here. So you construct the line passing through the origin in x0. Then the solution will be Schwaxxoliated symmetry means it's axially symmetric here. So if I take 2 points here at the same distance from this line, so the solution assumes the same value. And also I have the polar angle, okay? So it's non-increasing with respect to the polar angle. The angle is starting from this x here, this one, okay? So this is the Schwaxxoliated symmetry. So it means that you just lose one direction of symmetry because it's axially symmetric with respect to this line. Okay, and so the motivation to consider to write the 3 papers that I mentioned to you were mainly based on the nodal solutions, because about the positive solutions or the least energy solutions, many things was done. So by Bion and Wang and Kaopeng and Yang. So we consider this equation, the same Hénon equation, and our intention was to understand what happens about the symmetry of least, because the least energy nodal solutions, long time ago in 2003, Bart, Vet, and Willem, they proved that the solutions were the solutions are Schwaxxoliated symmetric, but they could not prove the symmetry breaking. Okay. Because any radial solution is Schwaxxoliated symmetric. Okay, but that's not true. Yeah, any radial solution is Schwaxxoliated symmetry because it's axially symmetric with respect to any line, and it's constant with respect to the polar angle. So the question from this paper from 2003 was about what can you say about the radial, the least energy nodal solution is radially symmetric or not? Okay, so this was the question that we want to solve long time ago, 2014. Indeed, the question was posed in 2003. Bart, Vet, and Willem said, okay, for alpha large, nodal solutions are not radially symmetric because we can use energy comparisons for radial solutions and the general solutions. And what I want to point out here is that if we have no weight here, we know that least energy nodal solutions are not radially symmetric. But the question that we pose, what happens when we have the weight x alpha? So I'm going to explain to you why these questions, the results for the autonomous case, or non-weighted case, cannot be applied directly to the case with the weight x alpha. Okay, so here are the questions. Which the precise symmetry of least energy solutions? Does alpha interfere on the Morse index of least energy radial nodal solutions? So just least energy nodal solutions is the solution with smallest energy among all the nodal solutions. But of course, we have the radial solutions. So, and among them, we can ask, or we may consider the least energy solution. And so this is the second question that we want to understand, to solve here. This is indeed the two questions, the two main questions of my talk. And we had some previous result on the symmetry breaking of least energy nodal solutions. As I said, Bart, Vet, and Willem, 2005. It's not, I was saying from 2003, that's wrong, from 2005. For alpha large, they knew that least energy nodal solutions are not radially symmetric. When alpha is small, Bonner, Ramos, Tavares, and myself, we proved in a more general setting that includes the particular case of the known equation, we proved for systems, Hamiltonian systems, that for alpha small, least energy nodal solutions are not radially symmetric. So this is only asymptotics, you see, alpha large and alpha small. But the question, the first question for general alpha was opened. And so let me represent here by M of U the Morse index of a solution U, N of U the number of nodal sets of a solution U, and in the case for any alpha greater or equals to 0, Bart and Vet from 2003, they proved that least energy nodal solutions have Morse index equals to 2. So among the, for the least energy nodal solution, the weight alpha does not interfere on the Morse index. So this result, indeed, some previous result on this direction for the non-weighted were proved by Bart, Chang, and Wang, and Castro, Cossio, Nobecker from 1997. This is one of the main reference for Morse index of semi-linear elliptic equations. Okay, then in the case for the Lane-Emden equation, when we have no weight here, in the case of alpha equals 0, Aftalion and Pacella, they proved that for radial nodal solutions, the Morse index of U increases depends on the number of nodal sets. Okay, and you see here, we know that the least energy nodal solutions have two nodal regions. So it means by this inequality, and so by this result by Aftalion and Pacella, we see that any radial solution has radial nodal solution has Morse index greater or equals to n plus 2. So since least energy nodal solutions always have Morse index 2, it's a corollary that least energy nodal solutions cannot be radially symmetric. Okay, and later this lower bound here was improved by the Marquis, Yanni, and Pacella in 2017. And this is the improvement on the Morse index of radial nodal solutions. And okay, then with phenomena in 2017, we started to think about, published in 2017, but in 2014, we were working, thinking about the symmetry, to prove the symmetry breaking of least energy nodal solutions. Okay, so let U be a radial nodal solution. What we proved with phenomena is that the Morse index of any radial nodal solutions is greater or equal to but this, just attention, I'm considering here n equals 2, dimension 2. So the Morse index is greater or equals to n, the number of nodal sets of the solution plus 2. This 2 comes from the dimension. And okay, for every alpha greater or equals to 0. Since we know that least energy nodal solution has Morse index equals 2, we proved here that least energy nodal solution cannot be radially symmetric, cannot be radial. Okay, so so we answered the first question that I posed some slides before. Okay, and we also proved that the Morse index depends on alpha, but we succeed only proving that for the particular case when alpha is even. You see here that the Morse index depends on alpha, also on the number of nodal sets, and it goes to infinity as alpha goes to infinity along the even powers. Okay, so this is, so what's the, just to emphasize some difference, Afitalion and Pacella in the autonomous case with no weight uses in a crucial way the fact that we derivate, if you derivate the equation partially with respect to xi, so you derivate this equation with respect to xi, so you commute the derivatives with the Laplacian. So they are indeed solutions of the linearized equation. L of this is the linearized operator calculated, evaluated in W, where W here will be the partial derivative. So this is when, if you go to the non-autonomous, when we have the weight x alpha, these arguments fails. So this property is a peculiarity of autonomous problem. And the proof of Afitalion-Pacella does not extend to the case of the Hénon equation. So let us move so this is, here I mentioned our contribution of phenomena. Then when our PhD that got the PhD degree here in our department, we succeeded on calculating the Morse index and proving some properties. So we consider a more general problem here, and this includes the Hénon equation, okay? And omega here is either a ball or an annulus centered at the origin of Rn. Just to recall, the Morse index of a solution of 1 is the maximal dimension of a subspace of H10 in which the quadratic form, so the second derivative of the energy functional, evaluating in the pair WW, is negative definite. Or alternatively, we can define as the number of negative eigenvalues of the linearized operator. Okay? And we also may, for a radial solution, we may define similarly the radial Morse index. We just substitute H10 by H10 rat. Okay. So given any continuous function, as before, n of u, the number of nodal sets of u, that means the number of connected components of this set here, x in omega, such that u of x is different from 0. And okay, so our results with Wendell in dimension n equals 2 again, for the known equations. Here is the unit ball in R2. So consider here the problem P alpha is the problem with weight x alpha, and P beta the problem with weight x beta. So let U alpha a radial solution of P alpha, U beta a radial solution of P beta with the same number of nodal sets. Then we prove the monotonicity of the Morse index with respect to the weight. So if alpha is less or equals to beta, then the Morse index of U alpha is less or equal to the Morse index of U beta. Okay, and how the proofs are? In addition, if we consider the radial Morse index, the radial Morse index is constant, does not depend on alpha, on the weight, but only on the number of nodal sets. So this is the radial Morse index. Okay, the proof is based on a change of variables. We could just like a power, okay? Take this transformation from R2 to R2, you give me y, and you put in the t kappa of y is this, like a power of the point y, okay? This transformation is very nice for dimension n equals 2, in the sense that the Laplacian behaves very well under this transformation. Here is it's very suitable for the Hénon equation in dimension n equals 2, because we can relate, choosing appropriately, let me just, choosing this kappa. If you give me alpha and beta, if I choose this kappa, I can relate the problem with weight x alpha to the weight x beta, y beta. I made the change of variable here. Okay, this is v using u and the change of variables. So I choose choosing this kappa. I will produce here the weight y to the power beta, just with a constant here in front, but this is not important. So you see that we may, with this change of variable, we may relate P alpha with P beta, and also with the standard Lane-Emden equation when we have no weight, okay? And this is the main ingredient. You see, we classify here the solutions. You see, if you give me a radial solution of the problem P alpha, if I use this change of variable, I have the solution of problem P beta, and with the same number of nodal sets. And this is from the both sides, okay? I go from P alpha to P beta and from P beta to P alpha, okay? And then we use again this change of variables. It was very, also helped us to calculate the Morse index. Here, look, if you give me again alpha less than beta, less or equal to beta, then what we could prove is, if you give me any test function for calculating the Morse index. Okay, I evaluate the quadratic form. The quadratic form with the index alpha is the quadratic form that depends on the solution U alpha. Okay, and here I make so you associate it to U alpha, as I said before. I construct U beta, then I have the quadratic form associated to the solution U beta, and we proved that we have this inequality here. It means that if you give me W such that this quadratic form is negative, again, the function W kappa is related to W using again the change of variables T kappa. Okay, and then I produce a direction where the quadratic form is negative. So if quadratic form of index alpha is negative at W, so the quadratic form associated with the solution U beta evaluated at W kappa will be negative. And this transformation T kappa maps linear independent functions to linear independent functions. Okay, and so this is how we prove the monotonicity of the Morse index. And if we restrict ourselves to the case of radial functions, so the Morse index will be negative with this quadratic form if and only if it's negative here. And so this is the reason that the Morse index does not change. The radial Morse index does not change. Okay? So this, the above proposition is the key for proving the theorem regarding the monotonicity of the Morse index. Okay, so just to make you to recall how the contributions for about the lower bounds for the Morse index. So again, we are in dimension n equals 2. You take alpha from the weight of the unknown equation. With Filomena, we prove that the Morse index is bounded from below by this number. Here is the number of node offsets of the solution. In the same paper with Filomena, when alpha is even, then we could improve this lower bound, showing that it depends on alpha. Okay? And then Amadori and Gladiali, as I said, they are doing very nice work on this equation. They improved our results with Filomena in two ways. They consider any power alpha, okay? And here they wrote the paper in dimension n equal greater or equals to 2. Here I'm just mentioning the results for dimension 2, and they proved this lower bound that improved our lower bound here. Then with Wendell, we could improve this lower bound for Amadori and Gladiali, and here is our lower bound, okay? And the improvement is based on also a result from Filomena and Yanni from 2017. We could prove that this number in blue here, okay, is greater than this number in blue here. You see that this part here are the same from both papers, and also here. Okay, so let me just give you the flavor to shift to the general case of n greater equals to 3. So consider again the case n equals 2. Let U alpha be a radial solution with m nodal sets of the Hénon equation. And then make this change a variable relating the solution of the Hénon with the solution of the Lane-Emden equation. Lane-Emden, so with no weight, okay? So, or if you want to make this, okay, or if you want to, so here R is, because we are talking about a radial solution, okay? So it depends only on one variable. You may write some T here, the same as above. So if you denote by R1 to Rm, the number, the points where the solution U alpha vanishes, so this at this point, at this point, at this point, okay? Then we have a direct relation between the nodal lines of the solution of the Hénon equation with the nodal lines of the solution of the Lane-Emden equation in dimension 2, okay? So in particular, as alpha goes to infinity, we see that all these points here goes to 1, okay? They goes to 1. They go to 1, okay? And also, you see by this relation here that the L infinity norm of U alpha, here is the L infinity norm of the equation, of the Lane-Emden equation. It depends on alpha precisely with this relation here. So it explodes. So this is the blow-up phenomenon, okay? And so this is the motivation. This I want to keep you in mind, that you keep in mind this behavior here, and also this behavior here as alpha goes to infinity. Okay, so the main result in dimension n greater or equals to 3, what we succeeded, and this I think it's interesting, that we could relate, you see, in dimension n equals 2, the equation, the Hénon equation is equivalent to the Lane-Emden equation using that change of variable that I showed to you, that kind of power, okay? And from this change of variable, we may obtain, it's the core of the arguments to prove the results that I showed you. Okay, but this is the equivalence. So in dimension n equals 2, this is, I would say, simple. In dimension n greater or equals to 3, that change of variable is not as suitable as in dimension 2, but it also helps. And what we proved that is the following. Consider the n-dimensional Hénon equation and the two-dimensional Lane-Emden equation. You see, the same power that we have here, we have here. So, Hénon equation dimension n, Lane-Emden equation dimension 2. So this is the main theorem. Let U alpha and W be the radial solution of P alpha and L respectively with M nodal sets. So fix the number of nodal sets, take a radial solution with this number of nodal sets here, and you call it U alpha. It's unique. It's unique. There is a result that it's unique up to sign, up to multiplication by -1. Okay? And take the solution of the Lane-Emden equation with the same number of nodal sets, radial solution. Okay? Then use this change of variable. This change of variable is the same as from the dimension 2. Okay? Then what we could prove is that this function V alpha converges to W in C101 intersection to C2 epsilon 1 for every epsilon between 0 and 1. So again, what we prove is that, okay, the limit problem for radial solutions of the Hénon equation in dimension n for n for every n greater equal to 2 is the same equation, is the Lane-Emden equation dimension 2. Okay, and from this we could prove interesting results. Okay, so the center of the proof is, as I said, the change of variable. And just to give you the flavor, when we make this change of variable V alpha, so we relate solution U alpha of the Hénon equation using this change of variable. So V alpha satisfies this ODE here. And you see that this seems to be the radial Laplacian. So this is the radial Laplacian at this dimension, if this was an integer. But even though it's an integer or not, you see that it seems to be the radial Laplacian. Okay, and just to show that why the dimension n equals 2 is the limit problem, because when alpha goes to infinity, m alpha goes to 2 as alpha goes to infinity. So this is, of course, we have to make many calculations to prove this result, but this is the sense for the proof. And from this, we could prove many other results. For example, the asymptotic concentration of the zeros and the blow up of the solution. We have very sharp results. So, for example, here, Ti is a zero of the limit problem, of the Lane-Emden problem, and Ri alpha is a zero of the Hénon equation. You see, as alpha goes to infinity, we have this limit here. In particular, as I said, all the zeros of the Hénon equation, these first zero, second, third, they have to go to 1. Okay, this is the consequence. We also have a blow up, how the solutions blow up. And for radial solution, we have a kind of local to global blow up, in the sense that if you give me, I'm sorry, I lost my, okay. If you give, so the solutions are posed on the interval 0, 1, because this is the absolute value of x. So if you give me any r less than 1, you see the solution blows up uniformly inside this ball. Okay? And this is the rate how it blows up. And this is more or less the behavior of the solution. We also improved somehow the best constant for the radial Sobolev embedding, the behavior of this constant with respect to alpha. We have this limit, so this improved the result by Vet, Smets, and Willem. And also, we proved some asymptotics for the Morse index, in particular, we proved that goes to infinity. And to finish, we also proved the monotonicity of the Morse index. Okay, I'm going to stop here. Thank you for your attention, and I'm sorry for being 2 minutes after the over the time that I had. Thank you very much.
Thank you, Professor Ederson, for this very nice talk and very interesting results. Let me see if we have some question or comments from the audience. Not for the moment, but I have one, if you allow me, Professor Ederson, just more for curiosity. And the results, you obtain nice results for the Laplacian, right?
Yes.
Yes. In the case of the P Laplacian, Ederson, how one could manage to try to obtain, because it seems that you use some linearization. How one can think about a Pila-Paschen version of the results.
Relating the radial solutions for the Pila-Paschen, I think it will be possible. However, Morse index for the Pila-Paschen, well, some people have introduced some arguments or definitions of kind of Morse index, but this question is by far open. Okay, indeed, I don't know, and this is a question that I tried to solve, and I still try to solve with a PhD student, about if the least energy nodal solution for the Pila-Paschen, if it's radial symmetric or not. I don't know how to prove. This is I would say that's a good question, and that I'd like to solve.
Okay, nice. Yeah. One more question, just for curiosity. And what would be the whole of the boundary condition? Let's say the result could be expected to hold for other boundary conditions, Neumann, Robin, or other. What do you think about it?
Yeah, Denis Bonner, our colleague and friend that will talk tomorrow, he has done interesting results for the Neumann problem. Okay, and also there is a paper by Gazzini and Serra that consider the non-equation for the Neumann boundary conditions. The problem became a little bit different, but they have interesting results that I would say that this is the starting point to think on this direction. They proved symmetry breaking for least energy solutions.
Okay, Professor Ederson. We have a question. Yeah, we have a question here by João Vitor da Silva. What happens in the fully nonlinear setting? Are there similar results, Professor, please?
That's a good question. Thanks for asking. The point I would say that everything here was based on energy. We were like talking about least energy nodal solutions and least energy solutions. And the question was like proving or disproving the symmetry of this special solution. So for the fully nonlinear, maybe it's my fault. I don't know how to define the energy, or maybe a different question. Maybe João Vitor have in mind. But yeah, I haven't thought about it yet.
Okay. Thank you, Professor Ederson. Thank you. It was a great pleasure to have you with us. Thank you so much for this very nice talk.
Thank you, Gustavo, and thank you to everyone in the audience. I could not see because here, Gustavo knows, I just see my screen here. Okay, thank you for your attention.
Okay, thank you. Bye-bye.
Bye-bye.
Okay, we will resume in 8 minutes. Thank you for joining us in this section, and we invite you to keep on going with us. Bye. Welcome to this last talk in this day, in this afternoon section in our UFSCar Workshop on PDEs 2022 online edition. It is a pleasure for me to introduce Professor Claudiano Alves from Universidade Federal de Campina, Grande, Brazil. Today, he's going to talk about existence of saddle-type solutions for a class of quasilinear problems in R2. Professor Claudiano is a fellow from the research agency CNPq in Brazil. His research interests lie mainly on variational and topological methods applied to elliptic PDEs and other topics. He has also been working as editorial board member in some research journals. Welcome, Professor Claudiano Alves. It is a great pleasure to have you in the workshop. Thank you for having accepted our invitation.
Okay, thank you very much, Gustavo. I would like to thank your invitation. For me, it's a pleasure to be here in participating in this very nice meeting. Okay. Today, can you see my screen?
Yes, Professor. Yeah.
Okay. Today, I will talking about this recent preprint involving existence of saddle-type solutions for a class of quasilinear problems in R2. This is a joint work with my PhD student, Hénon, and my colleague from Italy, Piero Montecchiari. Okay, here I show for you the outline of my lecture. Okay, I will talk a little bit one introduction, the one-dimension case, compactness properties, approximate and functional, and finally, I show for you how to build the saddle-type solutions and some reference involving this type of subject. So, and here I show for you the problem that we will talking about. Okay, the existence of a saddle-type solution for equation 1, and the equation 1 involve one quasilinear operator derived by one any function. The any function capital phi is given by of the primitive of this s time little phi here in the sentence 2, and this function phi or little phi is one C1 function that satisfies some technical conditions. And here I show for you this function phi satisfies 5 conditions. The conditions phi 1 and phi 2 are well known for this class of problem. Okay, this type of condition ensure for us that our Orlik Sobolev space that we will work are reflexive and separable. And the assumptions phi3, phi4, and phi5 are technical conditions that we need to use in your approach. The assumptions phi1 and phi2 were introduced by Fukagai, Ito, and Narukawa in this paper in blue here. And in this paper, Fukagai, Ito, and Narukawa is showed the Orlik Sobolev space is reflexive because the function capital phi and tilde capital phi are functions that satisfy one well-known delta 2 condition. Okay, but it's not interesting for us at the moment. Here I show for you some examples of any functions that our approach can be used. These examples are, in my opinion, very interesting because they appear in important physical applications, non-Newtonian fluid, plasma physics, plasticity, and nonlinear elasticities. Okay, for example, the first example is associate, for example, with a Laplacian operator when you fix p equal to 2. Okay, for more general p, we have the p Laplacian. the second operator, for example, we have the combination of one P Laplacian and Q Laplacian. And our approach is still true if you make one finite sum involving this type of any functions, okay? Related to the function v, because when you see our problem, okay, it's in some sense is one small equation. So, and you have the quasilinear operator, and we have here one potential v. Now I will show for you what is the technical hypothesis that we assume involving the potential v. The hypotheses involving the potential v are 6. Okay, when you see in the first moment, you can think this is a lot of hypotheses on the potential v. Here, these hypotheses are justified because we are trying to work with a large class of quasilinear problems. So we need to have one like very nice relation between the potential v and the any function capital phi. Okay, these two functions. Okay, it's a very important to have one very interesting relations. And here, for example, we have the conditions v1 and v2 are well known for this class of problem. And here we have this condition v3, v4, v5, v6. That these conditions are new for this type of problem, because I believe that this is the first paper that we try to prove the existence of saddle solutions involving one large class of quasilinear problem. So it is necessary to have one compatibility involving the any function capital phi with the potential v. Okay, so in order to show for you one simple example involving one potential v, I show for you this example. One very interesting example is v of t equal capital phi of modulo of t squared minus 1. Okay, this potential v satisfy all these conditions here. But this example is very, very important for us, because this example includes when you are working with the particular case involving the Laplacian operator, the well-known classical Ginzburg-Landau potential. Okay, this type of potential appear in a lot of problems, in particular in dimension 1. In dimension 1, in very, very papers involving the existence of heteroclinic solutions, this type of potential, okay, appear with some frequency. So the condition v2 and v3, I will show for you more one time, v2 and v3, okay, permit to prove, okay, that the potential v behaves like the function capital phi modulo t plus 1 when t is close to minus 1. And the second inequality, okay, ensure for us that the potential v behaves like capital phi of a modulo of t minus 1 when t is close to 1. This type of behavior is used, for example, when you try to find heteroclinic solutions for one dimension case involving one simplest ODE. Okay, so in some sense, we try to show for you what is the best relation involving the function, the potential v with the any function capital phi in order to prove the existence of heteroclinic solution and saddle type solutions. But for example, one heteroclinic solution is, for example, in our case, once that the potential v, okay, it's 0 at t equal to minus 1 and t equal to 1, one heteroclinic solution is one solution of this equation 1 that connect minus 1 to 1. Okay, for example, if you are in dimension 1, you ask, for example, that the limit of the solution when norm of t goes to, when t goes to minus infinity, the solution goes to -1. When the number t goes to plus infinity, the solution goes to 1. The main difficulty in general to prove the existence of heteroclinic solution and saddle-type solution, okay, is associated with the fact that this type of solution does not live in any Euler-Sobolev space or Sobolev space, because the solution go to 1 at infinity and go to -1 and minus infinity. So it is impossible, for example, these functions lives in L2, for example. So here I show for you the definition of the saddle-type solution. One saddle-type solution for equation 1 here is one solution, weak solution, of course, C1, by using the standard regularity theory for quasilinear operator, such that when they use the polar coordinate, you can prove that this function v satisfies this condition here. Okay, look, you have one anti-symmetry involving the half line theta equal to p sub 2 is the first information here. And the second one, you can conclude that p over g is one antiperiod in the angle variable for the function v tilde. Okay, the function v tilde is essentially the function v, but you consider v tilde the polar representation of the function v. It's a very interesting to observe that this saddle-type solution has this behavior here on this cone. Okay, for okay, this limit 4 said that the function goes to 1 when the whole goes to infinity. When you fix one line, okay, one line, theta constant, and theta in this interval here. Once that you have this information here, this behavior involving on this cone, when you combine this information with the information right here on 3, you can understand the behavior of the saddle-type solutions, okay? Later on, I will show for you one graph involving the interpretation of this type of solutions. But now I would like to talk a little bit about some papers involving the existence of saddle-type solutions. The first one that I would like to cite is Dan, Fay, and Pelletier. In this paper, the authors prove the existence of saddle-type solutions for one equation in R2, like equation 5 here. And of course, they assume some technical conditions, and the tool used here is the super solution method. Okay. In one interesting paper, Alessio, Calamai, Montechiari, the authors studied again the existence of solution for equation 5, again the existence of saddle-type solution, for another class of the potential V. And posteriorly, we have one paper by Alessio, Gui, Montechiari, where the authors established the existence of saddle-type solutions for one very, very interesting class of Allen-Kahn equations. Here, the equation 6. This equation 6 is a very interesting because this equation 6 generalizes the equation 5, because in the equation 5, you have in front of the derivative of potential V, the constant 1. But in this paper here, by Alessio, Gui, Montechiari, the authors work with a non-autonomous case, okay? In this paper, they prove the existence of saddle-type solutions. Look here, I show for you what is the characteristic of one saddle-type solution. And here the assumptions that Alessio, Gui, Montechiari used in their paper. Okay, we need to assume one positivity of the function A. We need to assume periodicity in the variable x, y. The function I is even with relation to the first variable, etc., etc., etc. Okay, it's very interesting hypothesis on the function A, capital A. But the literature involving the saddle type solution is not so much, but we have a very, very interesting papers involving this type of solution. In here, I show for you, okay, papers do Alessio, Montechiari, here Alama, Bronside, Guy, and so on, okay? Motivated by this literature, because when we make one review about the results involved the existence of saddle type solution, I asked to my PhD student, Renan Isneri, try to prove the existence of a saddle type solution for one large class of operator involving the operators deriving by one any functions. Okay, and in this case, we were able to prove the existence not only one saddle type solution, but many saddle type solutions, because give one integer j bigger than or equal to 2, it is possible to find one saddle type solution such that the solution Vj satisfy these 4 properties here, which characterize the fact that the solution is one saddle type solution. Okay, this is a very, very important characterizations involving here. But I would like to ask your pay attention involving this fact. If, for example, you to take j equal to 2, you find one specific saddle type solution. If you fix j equal to 3, you find another specific saddle type solution, and so on. For example, here, I would like to show for you this picture here. For example, when you fix j equal to 2, it is possible to find one saddle type solution such that in the first quadrant, the saddle type solutions, okay, the behavior of the saddle type solution, when you move on this green line, okay, the solution goes to 1 in the first and the third quadrant. But when you fix one line in the second and fourth quadrant, the behavior of the solution change. In this case, the solution, when you move on this red line, the solution goes to -1, okay? In all line that you fix here, in the second and the fourth quadrant, we have this behavior, okay? This behavior show for you, okay, like one saddle, because you have in this direction 1, 1, and another direction -1, -1. This is the case when you fix j equal to 2. For example, if you fix j equal to 3, the situation is more complicated, and of course, once that you increase the j, the situation is more complicated to build the saddle type solutions. For example, if j is equal to 3, it is possible to divide the plane R2 in 6 regions, in six cones, okay? Such that in 3 cones, the solution at infinite goes to 1, and another 3 cones, the solution goes to -1, for example. But this is a very interesting, because you can see that you have consecutive cones, the behavior of the solution change. For example, here, the solutions goes to 1 at infinity, but in this cone goes to -1. And the next cone come back to goes to 1. And the next goes to -1, and so on. This type of behavior is, in my opinion, is very, very beautiful, okay? And in my opinion, also the proof of this type of solution is not simple. Okay, and here we have one interpretations involving this behavior D by using another informations on the function. Okay, we have this information. This information I use it to show for you the pictures. But one very important point involving the existence of a saddle type solution involves the fact that in order to prove the existence of a saddle type solution, you need to know, okay, the properties involving the one-dimensional problem associated with your problem. Okay, for example, here it is necessary to study the existence of heteroclinic solutions from -1 to 1 for this one-dimensional quasilinear problem. Okay, this is a very, very important, because when we understand, okay, the set of the heteroclinic solutions, it is possible to build the saddle type solutions. What is the idea? Of course, the idea, for example, is to find one very interesting heteroclinic solutions. The resistance of heteroclinic solution is proved by using variational methods, but here the variation method is not so standard, because you use a minimization technique, but you need to fix one very nice set where this set is the candidate to have the heteroclinic solutions. And here we work with this functional phi on the set E, and we fix one subset of E, the set K, where the functional f a change minimum value on this E. Okay, and here we prove the existence of a heteroclinic solution for equation 7, sorry. Okay, and here it's a very, very important to observe that when we study the existence of saddle type solutions involving the Laplacian operator, when we consider this type of problem 7, okay, we arrive at one ODE. In this case, for example, we can use in some result the unique result involving ODE. But in your case, we cannot use, it is impossible to use the unique result for one large class of ODE like equation 7. But here it was possible to prove these very, very important behaviors involving the heteroclinic solution, and we prove the existence of one unique heteroclinic solution for the quasilinear problem in one-dimensional case, such that this heteroclinic solution satisfy these properties here. When we are working with the particular case involving the Laplacian operator, okay, you can prove the uniqueness of the result of one different way here. But here, this result was so hard, it's proved, because it was necessary to develop one new approach, new ideas, new estimate, in order to prove the existence and uniqueness result involving the heteroclinic solution for problem 7 here. Okay. Okay. Here, I mentioned for you that the heteroclinic solution has one long history and received special attention in recent years because this type of solution appear in many mathematical models associated with problems that appear in mechanics, chemistry, and biology, and so on. Okay, so the existence of heteroclinic solution is a very, very important topic that we need to study. Involving the existence of heteroclinic solution for this particular case of equation E4, okay, we have one rich literature where the authors study the existence of heteroclinic solution by assuming different conditions on the function A. And here I mention only this reference, of course. Okay, I'm sorry, it's impossible to see the one complete bibliography involving this type of problem. And here we see the one interesting paper do Bonnet, de Sanchez. We have a very, very interesting paper do Gavioli. Of course, we have a paper do Rabinovitz, okay, involving this type of problem involving the existence of heteroclinic solutions. For quasilinear problems involving the heteroclinic solutions, we have papers involving this subject. And here I would like to cite one paper do Minus, okay. And of course, we have one reference involving the existence of heteroclinic solution, who is the Professor Rabinovitz. This paper here that I show for you in this moment, for me, are very, very interesting. And this paper here was the first paper that I began to study when I tried to understand how to prove the existence of heteroclinic solutions. Okay? So here I would like to mention what is our challenge, okay, to prove the existence of heteroclinic solution for a large class of quasilinear operators. When we compare our problem with the particular case involving the Laplacian operator, it is very important to mention that when you work with Laplacian operator, you can use some very nice maximal principle. We have one rich literature involving maximal principle for Laplacian operator. You have you have in your hands C2 regularity, and you have existence and uniqueness of solution for second order of ODE. Okay, while in your case we cannot use this result because we have some difficulty to find this type of result. For example, of course, we don't have C2 regularity. For example, there is no one very nice existence and uniqueness of solution for one ODE involving one quasilinear operator. There is no. Here, it was necessary to develop new estimate by using, for example, Harnack inequality, C1 regularity by Lieberman, and one new uniqueness result for one ordinary differential equation deriving one quasilinear operator. Here, we prove one very interesting unique result that work very well in your case. This unique result cannot be used in one general situation, but in your case, it works well. So here I would like to mention the situations involving the one-dimension problem, because the one-dimension problem, okay, is the main point to build the saddle type solution, because we take the heteroclinic solution and using this heteroclinic solution, we build the saddle type solutions. So I will talk I will try to talk a little bit about this. Okay, you fix this set and you fix this functional. Look, the domain of this functional is not one traditional Orn-Sobolev space, but one W1 phi lock. And we work okay, on this set E, and we prove that, for example, that set E is not empty because we can show of one precise way one function that lives in that set. Have this information, this number C is well defined. And you prove some technical lemma. I will jump this technical lemma, okay, but it's very important because using these technical lemmas appear here in the right side of the inequality two important things for us: the number mu r and the function 8. When you get this number and this function, you can fix this lambda, this number lambda delta that satisfy this inequality. Okay, you can prove that this number lambda delta goes to 0 when delta goes to 0. And using this number, it is possible to prove this lemma 2.2. If you have one function in the set E, please, in the set E is the function that is odd. And this function lives in this Sobolev space in this log sense. And if you have one function such that the energy of this function with relation this functional is not so far off the number C, you have that this estimate involving the L infinite norm. Once that you have the lemma 2.2, it is possible to prove that if you have one function such that the energy of the function is equal to C, then the L infinite norm of this function must be less than or equal to 1. Now, we can prove that if the energy of the function is not so far off C, the modulo of K of T goes to 1 when the modulo of T goes to plus infinity. This lemma 2.4, okay, show for us that you have two possibilities, of course. The function K of T goes to 1 when T goes to plus infinity, or the function Q of T goes to minus 1 when T goes to plus infinity. This lemma 2.6 is a technical lemma involving, in some sense, minimizing sequence, and because you try to prove that the number C is achieved, okay? And you have this lemma in your hand. We prove that this set K here, given by in this sentence 10, is not empty. You prove that this K is not empty. One function that lives in K is one solution of our quasilinear problem. Okay, and what is the main difficulty is to prove that this solution is one heteroclinic solution. So we need to work more and more. Okay, this is a very, very hard part in the paper. Okay, to establish the behavior of this function Q at infinity, at minus infinity, because we intend to prove, for example, that Q for some Q and K converges to 1 when T goes to plus infinity, and converge to minus 1 when T goes to minus infinity. Have this in mind. We work a lot, and we prove, for example, this very interesting lemma 2.9. When you fix one function in the set K, okay, and we know that this function, okay, goes to 1 when T plus infinity, or goes to minus 1 when T goes to plus infinity. When this behavior, when the limit is 1, we call this number, this function Q plus. When the behavior for the right side is minus 1, we call this function Q minus. And we prove the following, okay? If the behavior at infinity is 1, this solution is increasing, this heteroclinic solution. If the right side, the behavior goes to minus 1, the heteroclinic solution is decreasing. Okay, here we have the one result involve the uniqueness of solution for this ODE involving one quasilinear operator. We prove the uniqueness, and using this uniqueness, we established a very, very nice information involving the set K. And of course, when you take, okay, when you get all these informations, okay, it is possible to prove the theorem 1.2. Of course, I am jumping here the technical part because there are more lemmas that I didn't show you in this lecture, but I show it for you only the main lemma and corollary, okay? But here, but one important fact in order to build the saddle type solution is to understand the compactness involving the minimizing sequence, okay? So here, again, it's a very, very important and difficult part in your paper, okay? Because when you try to prove this proposition for particular case involving the Laplacian, okay, the proof is not easy necessarily, but the proof is not so technical, okay? And here, some argument used for the Laplacian case cannot be applied for quadrilinear operator. So here, it was necessary to introduce one new argument, and here we introduce one new set, E tilde, one new number, C tilde. This set is very, very important because when we fix this set, E tilde, okay, and the number C tilde, it is possible to define one metric, and you can prove that this structure here is one complex metric space. Using this information, we were able to prove that this number, C tilde and C, are equals. Okay, with this equality, okay, we prove that that when you have a one minimized sequence, you can take another sequence, one PS sequence, but here PS sequence, I show for you what is the definition of PS sequence in your case, okay? Because here we are only working on one metric space. And here we prove the existence of one PS sequence close to the minimized sequence. And we prove that, in fact, that the approximated PS sequence is, in some sense, strongly convergent. Okay, so once that Qn is close to Pn and Pn, it's in some sense strongly convergent, you prove that the proposition 3.1. Okay. Here. Okay, we are close to finishing, and now we fix another setting. Okay, here we fix this set here of one OD function. We fix the same energy functional. We prove that this number CL is achieved. We prove that the number CL is less than of the number C. The number C is the number involving the heteroclinic solution. We prove that this set K is not empty. We prove that the existence of solutions for this problem here. And we prove this lemma 4.2, and I would like to talk a little bit about this lemma. This lemma is crucial. Okay, this lemma is crucial because after there is one important lemma that we need to prove that one set is not empty. And we were able to prove that the set is not able because we proved this lemma 4.2. Of course, this lemma is not ours, okay? The proof is totally different, but this lemma appeared in the previous paper do Alessio, Calame, Montechiari, Alessio, Gui, Montechiari. This now I show for you how we prove the existence of saddle type solutions. When you fix one inter number j, you fix this number aj, and you fix this interval, open interval iy, like this, and you fix this energy functional and this set E infinity. Okay? So here I show for you that this is the set gamma. Okay? It's one cone. Okay? It's one cone. This set here. So what is the idea? The idea is to prove the existence of one minimum of this functional J on this cone gamma. But the first challenge is to prove that this set E infinity is not empty. In this case, this lemma 5.1 apply one important rule in your approach, and this lemma is true because we have this very important behavior involving the level C and CL. Here, it's the CL, the CY is the same definition, okay? Because when you put here CL, you are working with one in open interval minus LL. So you prove that this number D infinity is achieved, and you prove that this function that achieves this number has this behavior here. This behavior, it is possible to prove when you have in your hand one uniqueness result, okay? After one very careful study, okay, we observe that it's not necessary to prove one very large unique result for the ODE, but one specific unique result that we can apply here in the lemma 5.2. So we conclude that the one function that satisfies this number is one solution, okay? Is one solution of the quasilinear problem on the cone, and using this function, we can build the saddle type solution. Please pay attention to how to build the saddle type solution. You fix this solution obtained in the previous sessions here, and you take these rotations here, okay? You fix these rotations associated with this angle here. So when you take this cone on this rotation, you will get more and more cones. When you rotation the initial cone, you get the second cone, the third cone, the fourth cone, and so on. Using these cones, you can prove that R2 is the union of these cones. So you can define your saddle type solution like this, okay? You take the function U bar, okay? That U bar is the solution obtained here in the lemma 5.2, and you take your saddle type solution by this sentence here. Okay, using this sentence, you can prove that this function is in fact one solution for your quasi-linear problem, and this function has the behavior that I showed for you in the beginning of my lecture. Okay, so here is only this reference because the other ones I showed for you. Okay, I stop here and thank you very much for your attention.
Thank you, Professor Claudio Nu, for your nice talk. Let's see if we have questions or remarks from the audience. Not for the moment, but I have one, if you allow me. Professor Claudio Nu, what could be expected in the case of functions phi not satisfying the delta 2 condition? For instance, exponential of t squared minus 1. For instance.
Yes.
Yeah.
Yes, this is my dream. In fact, it was my first go out with my PhD student. Okay, but I can say that the most part of the estimate in your paper is true without the delta 2 condition. Because, for example, the existence of the minimum on this admissible function can be proved by using the Schwaxxoliated topology, okay? But there is the result involving the uniqueness of the ODE for the large class of quasi-linear problem. Unfortunately, we need to use the delta 2 condition, okay? But I put in this challenge in the Hénon hands to try to prove the uniqueness of one another way, but I believe that it's so hard, and he will solve this problem probably after his doctorate.
Okay. Nice remark, Professor. We are seeing here some greetings from reactions from the audience. Thank you so much. And I thank you so much, Professor Claudio Nu, for this interesting talk. It's a pleasure. It was a pleasure, in fact, to have you with us in the workshop. Thank you so much.
Okay. Thank you for your attention. For me, it's a great pleasure to be here, because for me it's a very nice opportunity to see you and other friends, Olympio, Odaí, etc. Okay. Thank you for your attention.
You. My pleasure. Our pleasure, Professor. Thank you so much. Bye-bye.
Bye.
Okay, this lecture from Professor Claudio Nu closes our activities in this day in the workshop. Tomorrow we will resume at 9 a.m. São Carlos local time with the lecture of Professor Patrizia Pucci. The links for tomorrow can be found at the website of the workshop. Please visit there. Thanks for joining us today, and I hope to see all of you tomorrow. Thank you. Bye-bye.